Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 5, RK Bali navigation book. The book that I am referring to is the fourth revised edition. But if you happen to have any other book of any other revised edition, no problem. The questions are just the same, whether you take fourth revised edition, the fifth one, or the sixth one. So let's begin with question number 21. Course as wind speed is given to you. Maximum drift angle that will be obtained will be from a wind direction of what value? So maximum drift angle, meaning maximum crosswind, will be obtained from what kind of wind direction, right? So crosswind formula is whatever wind speed into sine theta, where theta is equal to wind direction minus your course direction or runway direction. So here the course that you are flying is 095 is 095. Course 095. TAS is 220 and wind speed is 70 knots. So maximum drift angle will be obtained. So there is first direction given to us is 165. Okay. So if winds are coming from 165 degree, that means somewhat from this direction. Okay, wind velocity 165 degree at 70 knots. So in this case crosswind will be equal to wind speed into sine theta, right? Wind speed is 70 knots. Sine theta value will be wind direction 165 degree minus the course that is 95. So sine of 70. Next, let's explore the second option. The second option states the wind is coming from 185 degrees. 185 degree means, let's say this is your course of 095, course 095, and winds are emanating from 185 degree. So something like this. So wind velocity 185 at 70 knots. So in this case, the crosswind will be wind speed into sine theta, 70 into sine of 185 minus course 95, sine 90. In the third option that they have given, again, course is 095, winds are blowing from 215 degrees. 215 is, it will be something like this. Okay, wind velocity 215 at 70. So crosswind will be equal to wind speed into sine theta, 70 knots into sine of 215 minus 95, sine of 120. So let's solve this. Sine of 70 is 0.939 or whatever. Multiply that by 70, it gives you a wind speed of 66 knots approximately, crosswind of 66. When you come here, 70 into sine 90, you get a crosswind of 70 knots. Going further, sine of 120 into 70, you get a wind speed of 61 knots, a crosswind of 61 knots. So the maximum crosswind value here is 70 knots, and it belongs to the wind which blows from 185 degree, that is southwest direction. Okay, so the correct answer here will be maximum drift angle. Okay, maximum. So maximum crosswind will engender maximum drift angle. So here the wind direction is 185 degree. I have shown you all the three options, three crosswind components, 66, 70, 61. Maximum being 70, the wind direction coming from that particular direction of 185 degree will produce maximum drift angle. Next, when climbing through an isothermal layer at constant Mach number, what will happen to calibrated airspeed and true airspeed? So here is your air mass. Okay, here is your air mass. Isothermal layer means temperature is going to be constant. The temperature is going to be constant. Okay, let's say this is that constant isothermal layer air mass. Okay, and you are climbing in this particular air mass. Climbing in this particular air mass like this. Okay, isothermal layer, iso layer, let's say 20 degrees Celsius. Now what will happen to your calibrated airspeed? Very simple. When you climb to higher altitudes, atmospheric pressure decreases. As a result, dynamic pressure registered in your ASI equipment, airspeed indicator equipment, will also decrease. It will also decrease, and therefore calibrated airspeed indication will fall as you climb to higher and higher levels. Okay, in order to correct this situation, in order to correct this situation, that is, prevent the calibrated airspeed from falling or from decreasing in value as you climb, you must increase or accelerate the airspeed of your aircraft. This acceleration will produce compensating dynamic pressure, that is more dynamic pressure. This dynamic pressure will be registered in the ASI equipment, and your calibrated airspeed will not fall. It will remain stable, okay, or it will increase. It will produce compensating dynamic pressure. So this is what happens. So correct answer is, when climbing through an isothermal layer at constant Mach number, your calibrated airspeed should decrease, because atmospheric pressure goes on decreasing as you go to higher levels. and if you climb at same speed, same Mach number speed, in isothermal layer, when you climb at same Mach number, you are also climbing at same true airspeed. So when you're maintaining that true airspeed, constant true airspeed climb, calibrated airspeed will suffer. It will decrease because atmospheric pressure surrounding aircraft around the pitot tube will also decrease. The dynamic pressure required to produce to sustain that calibrated airspeed will not be sufficient, and therefore calibrated airspeed value will decrease. To maintain that same calibrated airspeed value which was existing on previous lower altitudes, you will have to increase the true airspeed of your aircraft so as to compensate for that decrease in dynamic pressure, static pressure as you climb to higher altitudes. Okay. Question number 23. When descending through an isothermal layer at constant calibrated airspeed. So again, the layer given to us is an isothermal layer. An isothermal layer is a layer of constant temperature, let's say 20 degrees Celsius. Okay, this is your aircraft and you are descending to a lower altitude at constant calibrated airspeed. At constant calibrated airspeed. Now, when you descend at constant calibrated airspeed, what happens? Now, when you are descending to lower and lower altitudes, what happens to atmospheric pressure? The atmospheric pressure increases, right? So, when you are descending at a particular calibrated airspeed to lower altitudes, the atmospheric pressure getting increased will result in your calibrated airspeed getting increased in value. So, increasing atmospheric pressure will increase the value of your calibrated airspeed in your airspeed indicator. So in order to maintain same calibrated airspeed throughout your descent, to maintain that calibrated airspeed value stable, you will have to decrease true airspeed of your aircraft. When you are climbing, and in order to maintain that stable calibrated airspeed, to prevent it from falling down, you increase the true airspeed of your aircraft. In descent, you will do the stark opposite of it. You will decrease the true airspeed of your aircraft because coming down, you encounter or you experience higher atmospheric pressures. Higher atmospheric pressures will translate into more calibrated airspeed getting registered. And we do not want that. We want to maintain constant, stable, calibrated airspeed. So we will have to decrease some other factor which will help us achieve this. And what we decrease is our true airspeed. But here the options are with respect to local speed of sound. The local speed of sound ka formula is 39.17 square root of temperature in terms of Kelvin. So local speed of sound is directly proportional to temperature. Warm temperatures, more temperatures, hot temperatures, more will be the local speed of sound. Cold temperatures, lower the temperatures, lower will be the local speed of sound. So now in this isothermal layer, the temperature is going to remain the same, 20 degrees Celsius, whatever, 30, 40, whatever. So throughout this isothermal layer, as long as you are flying in this isothermal layer, the local speed of sound will remain the same, whether you are flying at 4,000 feet, 5,000 feet, or whatever altitude. As long as you are immersed in this isothermal air mass, the local speed of sound will also remain the same because the temperature remains the same. The temperature here is the governing factor. So local speed of sound remains constant. Next, how will Mach meter indication respond if aircraft is flying at a constant calibrated airspeed at 27,000 feet when it experiences a reduction in outside air temperature? So this question has something to do with this concept of local speed of sound being proportional to temperature. Now Mach number is true airspeed divided by local speed of sound, which is true airspeed divided by 39.17 square root of temperature in Kelvin. Okay. Next. So you are flying at a constant calibrated airspeed. So here is your aircraft. Okay. Currently it is flying at a constant calibrated airspeed in an air mass, in a warmer air mass, somewhat like this. In a warmer air mass. And now soon, very soon it transitions or enters a cold air mass where the outside air temperature will be less, will be okay, will be very low. Calibrated airspeed. Let's say calibrated airspeed of this aircraft is 200. Pressure altitude is 27,000 feet. At 27,000 feet, ISA temperature ought to be what? So it must be 15 minus 2 into 27. 15 minus 54. 15 minus 54 is minus 39 minus minus 39 degree Celsius. Minus 39 degree Celsius. Okay. When we put these values in the CX3, so let's facilitate. I will put these values in the CX3. Calibrated airspeed to airspeed option. TAS is the TAS is not given to us. Fine. Calibrated airspeed 200. Pressure altitude 27,000. And outside air temperature is 39 minus 39. So put 39 value and then press this plus minus button. So it's minus 39. In this case, you get a TAS of 360 knots and Mach number 0.5. Mach number 0.508. Okay, now from this air mass, this warm air mass, your aircraft will enter this cold air mass. Okay, it enters this cold air mass, and in this cold air mass, again, a few conditions remain the same, like calibrated airspeed is 200. We have considered it 200. Pressure altitude given in the question 27,000 feet again, and ISA temperature at 27,000 feet must be minus 39 degrees Celsius. But we have considered that, as given in the question, aircraft experiences a reduction in outside air temperature. That means it is experiencing colder temperature. So let's take any temperature colder than minus 39 degrees Celsius. So any temperature colder than minus 39 is, let's say, minus 45. Okay, minus 45 degrees Celsius. Now let's put these new values in your CX3. Outside air temperature is 45 minus 45. Okay. Calibrated airspeed 200. Pressure altitude 27,000 feet. So in this case, what's happening? TAS is 360 and Mach number is 0.612. TAS is 360 and the new Mach number in this cold air mass is 0.612. So what has happened? Mach number has increased from 0.5 to a new Mach number of 0.612. This Mach number in colder air mass is much more than the Mach number you were flying at in warm air mass. So the result is, well, how will Mach meter indication respond? The Mach meter indication will increase. There will be no change. There will be a decrease. There will be increase or decrease depending on total air temperature. So the most suitable option is Charlie. Okay. It can increase. It can also decrease depending on total air temperature, the outside temperature, how much the outside air temperature is colder. Okay. So 24 is Charlie. This is how I have explained to you the concept. A Mach meter comprises of a combination of ASI and altimeter. What is a Mach meter? It is a combination of altimeter and airspeed indicator. Next, question number 26. Aircraft is flying at 310 knots through airspeed at flight level 310 knots to airspeed flight level 290. Temperature deviation is given. What is local speed of sound? We all know local speed of sound is 39.17 square root of temperature in Kelvin. Now we are flying at flight level 290. The temperature at flight level 290 must be 15 minus 58, that is minus 43 degrees Celsius. ISA temperature 29,000 is minus 43 degrees Celsius. Deviation given to you, ISA deviation is nothing but outside air temperature, ambient temperature minus ISA temperature. So deviation is minus 6 degrees Celsius. We do not know outside temperature. ISA temperature is minus 43. So outside air temperature will be minus 6 minus 43. So outside air temperature will be minus 49 degrees Celsius. Minus 49 is nothing but 224 Kelvin. So let's put this value here. 39.17 square root of 224. Square root of 224 is 14.9 of 15. 39.17 cross 15. That is 586 knots. 586 knots. So the closest option here will be option Bravo. 583 knots. Increase of 0.15 in Mach number results in an increase of 93 knots TAS. Temperature deviation is minus 9 degrees Celsius. What is the altitude flight level aircraft is flying at? Mach number equals to TAS divided by local speed of sound. Now Mach number of 0.15 is equal to TAS of 93 divided by local speed of sound. So local speed of sound is 93 divided by 0.15, 620 knots. Now what is local speed of sound? It is 39.17 square root of temperature in Kelvin. So we have a speed of sound equal to 620, 39.17 square root of temperature Kelvin. So that is cross multiply again. 620 divided by 39.17. That is 15.8. Let's consider 16. So temperature will be 256 Kelvin. Now 256 Kelvin is 256 minus 273 minus 17 degrees Celsius. Now we have to find out the level. We have to find out flight level. Now outside air temperature is minus 7 degrees Celsius. ISA deviation is nothing but outside air temperature minus ISA temperature. Deviation given to you is minus 9 minus 7 minus ISA. So ISA will be minus 7 plus 9, that is 2 degrees Celsius. So ISA temperature is 2 degrees Celsius. You are supposed to find this 2 degrees Celsius at what altitude? You will find 2 degrees Celsius at an altitude of, let's say, 2 degrees Celsius. The formula is 2 into altitude or flight level. So degrees Celsius minus 15 degrees Celsius equals to minus 2x, where x is the altitude. So minus 13 equals to minus 2x, x is equal to 13 by 2, that is 6.5 or 6,500 feet. 6,500 feet. Now the closest option here is 9,000. So I'll select that option, option Charlie. Okay, so this. So ISA temperature will be minus 17 plus 9, that is minus 8 degrees Celsius. Now minus 8 degrees Celsius, you will find this at what altitude? 11,500 feet. And minus 17 degrees Celsius. Okay, so minus 8 and minus 8 degrees Celsius is found at 11.5, that is 11,500 feet, and minus 17 degrees Celsius, minus 17 degrees Celsius, you will find at 16,000 feet. You will find at 16,000 feet. So the closest option is 20,000, 22,000, flight level 900. Question 28. Distance A to B is given to you. Outbound speed, homebound speed, endurance is given. What is the time to the point of safe return? So we will first find the distance to the point of safe return. Distance to the point of safe return is endurance into outbound speed into homebound speed divided by outbound plus homebound. So what is endurance is 8 hours 30 minutes. Outbound speed 480, 420. 480 and 420. Distance to PNR will be, so 480 into 420 into 8.5 is 1713,600 divided by 700 is 2448 nautical mile. Time to PNR is distance to PNR divided by outbound ground speed. So 248 divided by outbound speed is 420. So 5 hours 49 minutes. 5 hours 49 minutes, that is equal to 5 say 300 349. So 5 hours 49 minutes. 349 minutes. So closest option, I think there is a mistake in the 8. It should be 349 actually. 50. So here the values are ground speed outbound 420, ground speed back 480, safe endurance time from A to point of safe return is 28 C. 272 minutes. So 480 into 420, 480 into 420 into 8 hours 5 minutes, 1713,600. 480 plus 420 is 900. So correction. Distance to PNR is 900. So 1713,600 divided by 900 is 1904 nautical miles. Is 1904 nautical miles. 1904 divided by 420 It's 272 minutes. It's 272 minutes. Option alpha. Next, similar question. Distance Q to R is given. Outbound speed, homebound speed is given to you. The time from departure to the point of equal time is what? So now we have to find, first we have to find distance to point of equal time or critical point, that is total distance into homebound speed divided by outbound plus homebound. So total distance is 1760, homebound speed is 360 divided by 360 plus 450. 360 plus 450 is 810. 1760 into 360 is 633600. So distance to point of equal time will be 782 nautical miles. So time to point of equal time will be distance divided by outbound speed, 782 divided by outbound speed of 450. 782 divided by 450 is 1 hour 44 minutes. 1 hour 44 minutes or 104 minutes. Option Charlie. Question 30. Distance A to B, outbound speed, homebound speed. We have to find time from point A to the point of equal time. So let's first find distance to critical point, which is total distance into homebound speed divided by outbound plus homebound. So 3600 into 400 divided by 400 plus 378. 400 plus 378, 778. न्यूमरेटर में 3600 into 400, 1441123 So that is equal to critical point distance is 1851 nautical miles. Time to that distance will be 1851 divided by outbound speed 378. 4 hours 53 minutes or 293 1851 divided by 378. 293 minutes or 294 minutes. The closest option here is option Charlie, 288 minutes. So with this question, we come to the end of this lecture. I hope you have understood all the questions that I have done in this particular video lecture. If you have any doubts, questions, query, let me know in the comment box of this video. I request you all to share this video with all your friends. I subscribe to this channel if you haven't yet, and like the video lecture if you have liked it. In the next video lecture, I will be solving the next 10 questions. So don't miss that. Let's meet there.